Alright, so I have a box. That box is sitting on a flat surface, so the first thing I want to do is I want to draw myself a free body diagram. It says a horizontal force 50 newtons is required to pull an 8 kilogram block of aluminum at a uniform velocity across a horizontal wooden desk. What's the coefficient of kinetic friction? Okay, so I need to find the coefficient of kinetic friction. Now, first thing you want to ask is, what's coefficient of kinetic friction? Well, the coefficient takes into account the two surfaces that are rubbing against each other. So it's just a given value to you. In this case, we can solve for it, but it may may allow you to determine, well, what are the two surfaces that are actually rubbing against each other? Okay, so we do see that it's aluminum. Maybe it's, and it does say a wooden surface, doesn't it? A wooden desk. So if there was on that chart a aluminum and wooden desk, we might be able to see what the actual coefficient of friction is. And again, what a coefficient is it takes into account two certain variables and it compares them based on something else. All right? So if I'm looking at this question, let's just discuss what's happening by looking at a free body diagram. All right, first things first, forces acting on this free body is what? 8 newtons. No, just identify them just from here.
Gravity and normal.
Okay, so the force of gravity works that way, right? And what holds it up? Normal force in this case, it's a book on a desk or on a surface, right?
Question, quick word.
Bottom of the page, sample problem. Okay, so now it says that it's being pulled. So that force we call what? Well, we call it an applied force. If there was a rope involved, I don't know if it says there's a rope involved. If there was, you could call it tension. Wouldn't matter. All right, but we'll say that it's an applied force. And then what's working against it?
Force of friction.
The force of friction is working against it in this direction here. Okay. Now, we've done this in the past. We've talked about net forces, or not net forces, but we've talked about net direction when we talked about vectors, right? So we took into account the horizontal, so the vertical, and the horizontal aspects of the components of those vectors, right? Well, in this case, if I look at the force of gravity and the normal force, is the box moving up or down at the moment? It's staying the same. So what's the net vertical force in this case? Zero. So there's no net force on that. So then what we do is we say, okay, well, what direction is the box moving?
It's not right now, but when it does start moving, it's going to be moving horizontally.
Horizontally? Which force of those four forces
To the right.
shows us which one it is? Fa. Fa, that's right. My applied force. And then I would subtract my force that's acting directly against it, which in this case is force of friction. Okay. So in the question, I want to find what my force of friction is, because it gives me, this is 50 newtons, right? It doesn't give me the force of friction. Does it give me a mass or an acceleration on this?
8 kilograms.
8 kilograms.
Mm-hmm.
But does it give me an acceleration?
Force divided by mass, acceleration.
Yeah, but I don't have a net force and I don't have an acceleration. All right, so I'm looking at this question right now and I'm saying, wait a minute, I'm missing a piece of information. I either need to know the force of friction or I need to know the acceleration, right?
Right.
However, the question just simply asked you to find out what the coefficient of friction is. So yesterday I told you force of friction is equal to the normal force times the coefficient of friction. All right, that was the first new, well, I shouldn't say the first because I talked about tension too. But go ahead.
So what is that?
It's like the micro, right? and with a little f that identifies it as coefficient of friction. Look at the top of 163 on that chart.
Oh, some little.
It's just a symbol.
Yeah,
Okay, the K represents kinetic, which means it's moving. Let's just put it as F, so we know it's coefficient of friction. Okay, so looking at that, then I want to isolate what the coefficient of friction is. So how do I get this guy by itself? What do I do? Divide Fno. Very well said, right? Equals force of friction over my normal force. Agreed? So far, so good? Okay. A horizontal force of 50 newtons required to pull an 8-kilogram block of aluminum across a horizontal wooden desk. What is the coefficient of kinetic friction?
Oh, yeah.
Okay. It says a horizontal force is required to pull. So an initial force, I need to pull. So what they're saying then is they treated this question as if this right here was 0. Okay? They're saying then if it's at rest right now, then the force of friction must be equal to the applied force, right? If it's just sitting there, therefore the applied and the force of friction were equal. So that's the part we missed right here. Okay? So now, that's 50 newtons. Subtract FF. Therefore, my force of friction in this question is equal to 50 newtons. Okay? Because that box wasn't moving, it was just sitting there, then the applied force and the force of friction have to be equal to each other. Now, in theory, your frictional force could be greater than your applied force, but for what we're doing is we're just going to assume then that it was equal to each other because it's not moving. All right, that's the minimum the force of friction would have to be to stop it from moving. It's the same as the applied force. So now I know that. So I go 50 newtons then, and I have to divide it by my normal force. Well, what does my, go ahead, Brock.
Well, it would be 0, right? 'Cause it's just standing still. But if I guess, if the table has a force, or the gravity has a force going down, so there has to be a force pushing it up.
There's a force, the net
Sorry,
force
this
is
not
0.
finished. Not
Yeah,
finished.
the force would be the same as the gravity.
Yes,
Yeah.
that's exactly right.
Good man.
Very good. So this force and this force, if they're not moving up or down,
Same thing.
must be the same. Can we calculate the force of gravity?
Yeah.
Yeah, because I have a mass, which is
50 or 8.
8, and I have a acceleration, which is
9.8.
9.8. So let's take 50 newtons and divide it by 8 times 9.8. You need brackets for it. Go ahead, Alexander.
0.638.
Perfect, thank you. And there's no units on that because this works out to newtons here, and you divide them, you're going to end up with a coefficient of friction. So what did that tell us? That says that the coefficient of friction between an aluminum whatever and a wooden whatever, when they rub together, they're going to have a coefficient friction of 0.638.
That's my one.
That's the final answer for that question.
No units to 68. Maybe.
Right. Right. Okay. All right, so far? Okay. So new to you today, this is the first time that we've used this right here. That's just force of friction divided by normal force equals the coefficient of friction. All right? We okay with this?
How did he get 0 newtons?
It was just sitting at rest here.
Oh, so
Yeah. Okay. All right. Now it doesn't actually say that in the question, but we
Yeah.
assumed it was. Okay. All right. Let's look at this next part. The driver of a 2,000 kilogram car applies the brakes on a dry concrete roadway. Calculate the force of friction between the tires and the road surface. Okay. I don't think I need to do this question. It's the exact same question. Except they, okay, so they're looking for the force of friction between the tires. I got a coefficient of friction here. Oops. I've got this times this, right? So a car is just resting on the road. Therefore, the normal force is equivalent to what? Look at your diagram. What's the normal force? Or sorry, what's the force of gravity equal to?
-9.8.
Normal
Okay.
force.
Yeah. So the normal force is equal to your force of gravity. That's right. Right? Okay. So then, how much? What was the mass of that car?
2,000 kilograms.
2,000 kg. And I got 9.8. Right? Now I got to go back to my chart and find out what the force, the coefficient of friction is between rubber and
Concrete. Right?
dry concrete.
As if it's doing some driving.
So what is it?
1.02.
1.02. And you multiply those all together, and you'll get the force of friction of a car resting. So what does it work out to? So we'll take 2,000 times 9.8, so 19,600 times 1.02.
19,992. Good enough.
19,992.
92.
Okay, good. All right, so far? Okay. So again, not new. All right, this next question is one of the questions that you had on your assignment that you handed in. Okay? A 20, except it was the train question, similar to the exact same way you do that question. 20 kilogram box is dragged across a level floor with a force of 100 newtons. The force is applied at an angle of 40 degrees above the horizontal. If the coefficient of kinetic friction is 0.32, what is the acceleration of the box? All right. This question, we did it with a train, right? There's a railway car, okay? It was pulling off to the side like this. Our applied force is right here. Okay, remember this? So now it's 40 degrees with the tractor, that's right. There's a tractor pulling it. Okay, so now, here's what we have to do different than that question. Oh, I don't want to put that there. I want to put this here. Okay. All right, so it's being dragged across the floor with 100 newtons. All right. First thing I do in all of these questions, net force. What direction, what's the force of direction, or what direction is the force moving this object? Which force are we using here? The applied force. So I don't know it, so hopefully I can find it. And then what's holding it back? Force of friction. So same hole, right? Same thing happens again. Applied force, net force equals applied force minus force of friction. All right, so the first thing I want to do is I want to find the applied force then. So let's look for the applied force. How do I find the applied force right here?
Cos 40 times 100.
Cos of 40 times 100. So let's do that, please.
76.604.
624?
604.
604. Thanks. Okay. Now I want you to find. Now I mentioned this the other day. We didn't deal with it before, but we may have to deal with it today. So I'm going to ask you this. When I'm pulling something, and I'm pulling on an angle like this, so think of yourself pulling a wagon. Okay, so the wagon's down on the ground, right? It's on the floor, but at some point there must be a little bit of lift, isn't there?
Yeah.
Right? Unless I'm pulling it straight horizontal, there's got to be a little lift. just the same as if I'm pushing on a lawnmower, there's a little bit of push down, right? Okay? So let's find out what force I'm going to lift that wagon with.
Okay.
So let's find this, I'm going to call it a vertical force here. So can you find that vertical force for me right here, please?
Oh, it was like 64.
0.279.
Force vertical, 64.279 newtons. So far, so good?
Yeah.
Okay, any problems with the triangle part of this?
No.
So we all understand that if I'm pulling something and I'm pulling it on a slight angle, that there has to be a component that says it's going to lift up off the ground, right? Okay. Now, let's ignore anything else that's in that book right now. My question to you is this, okay? We identified that there's a force applied and that force applied is going in this direction, right? And then I have this force of friction that's going over here, so I need to find that at some point as well, okay? But what are the other forces that are acting on that wagon now? Okay, gravity for sure, yeah? There's going to be a force of gravity, right? What is the other forces acting on it?
Normal force.
There's a normal force, right? And which way is the normal force going? Right, so that's normal force right there, right? Okay? And what's the other force that I just calculated?
Vertical.
The vertical force. And which way is it acting?
Up.
It's acting up, isn't it? So it also goes up in this direction like this, right? So far, so good? We following so far? All right. I want to ignore the horizontals for a second, and I just want to talk about the vertical for 1 second here. Okay? Now, in all the questions that we've done up to this point, and I said that when something was sitting on a horizontal surface, that the gravitational force and the normal force, they canceled each other out, right? Because I got zero out of that, right? Okay. Now, the normal force is located right here on the ground, underneath the wagon. Fair enough? So the force of gravity is pulling it down. So let's find out what the force of gravity is. What's the force of gravity? Do they give you the mass of that wagon?
Yeah.
20 kg. What's a box, I guess, eh? 20 kg. So then that makes this 196 newtons, right?
Yeah.
9.8 times 20. We're okay so far? Okay, I want you to look at the board now for a second. If I had no vertical force there, if I wasn't lifting up on the box, what would the normal force be equal to in that question?
196.
It'd be equal to 196, right?
Yeah.
Right? But because I'm actually helping the box up a little bit,
Same.
will the normal force be higher or lower than if I'm lifting it up?
Lower.
Lower. No, lower.
Okay, where is it located? It's located down here, right? It's pushing from underneath here, right?
Oh.
So if it's pushing
Yeah,
from underneath
so
and then I lift it up a little bit,
Here. It's fine.
No, the normal force just lowers to keep it on the
you're
ground.
going to do a Papa Louie at the very least, right? Okay? So then, in other words, what does the normal force equal in this question?
FG minus FV.
Yeah.
You take the 196 of the gravity pulling it down, and then you would subtract the amount that I'm lifting it up with, right? That would give you my normal force. So take 196 and subtract 64.279. Alexander, go ahead.
131.721 newtons.
I did something similar, did you guys do that minus the extra vertical?
Yeah.
Would be behind the word.
What's wrong?
No, we just did this question wrong, I think.
Well, we're thinking like it's kind of like the question on the test, or
Oh, no,
assignment, so,
ignore the test. This is completely
Okay.
different now.
okay.
Just the setup of it was the same.
And I was like, man, I did that
Oh.
question so wrong.
Yeah.
All right, so we all understand what happened here? That if I'm lifting up on, so let's say I reverse the role now, and I say I'm pushing down on the lawnmower, and this vertical force is pushing on the ground.
Did you add it?
then what would happen? Yeah.
Yeah.
Then what would happen with the normal force? You'd have the force of gravity going against it, but you'd also have what? Exactly. The vertical force would be going against it. So you would then add them together. So just wanted to show you that. Okay? That's what happens in this question. Now, why is it so important I'm focused on the normal force? Because that's how I get my force of friction. All right? So in this question it says, we're dragging. If the coefficient of kinetic friction is 0.32, what is the acceleration of the box? So again, I go back to this. What's my mass? 20. I want my acceleration. My applied force in this question is 76.604, right? And I have to subtract my force of friction. So my force of friction is my normal force, which I calculated to be what?
131.721.
131.721.
But then you wouldn't move it.
That's my normal force, right?
No, because you still
Extremely
have to
negative.
Oh, wait, yeah.
And then I'm going to multiply it by my coefficient of friction, which is given to me as 0.32.
Mm.
Yes, Austin, if there was no coefficient of friction, you'd be right. It wouldn't move.
Okay.
Okay? But there's a coefficient of friction. So now what I do is I take 76.604. I subtract 131.721 times 0.32. And then what do I have to do last to get acceleration by itself? Divide by 20. So do this part first, hit equals, and then divide by 20, and you should get your acceleration.
I'm gonna divide by what, 20 you said? Or divide by 20 by that?
No, divide by 20.
So 1.723?
Yes, that's right.
What?
You probably didn't do brackets, so it's just like messed up.
Okay, so, Amron, watch please. Type that in, 76.604. Subtract
131.721
times.
Oh,
Yeah, but
those are in brackets.
No, you
together.
can't hit equals,
They're in brackets.
because then it would do this, subtract that, and then times. You can't have that, right?
So
So then you just put it all in as you look right here, put it all in like that. Hit equals after that, and then divide by 20. Or you can put brackets around all of them. Okay. How we doing? So
average.
we did this question already. We did this question, right? We've done the questions where we pulled something. We've done the shovel questions. We've done the lawnmower questions. So the only thing that we add on to what we have already done
And the coefficients.
is the coefficient of friction and your normal force now. That's what we've added on to the question. So everything's done the same way, except we now add on the normal force.
On vertical.
And vertical force. Yeah, that's right. Okay. We all right so far? Okay.
Vertical force is always not that bad. Side of the triangle or whatever.
Yes. Okay. Next question. Again, this one is identical to question 1 and whatever the last question was on that assignment. We have a toboggan going down a hill. So those of us that did not do it right probably want to pay attention and write it down again.
What's the exact same one?
Okay. So I have a toboggan on the side of a hill. It's going to go down the hill because what's going to pull it down the hill?
Gravity.
Gravity. In which direction does gravity work?
Straight down.
Straight down.
Yeah.
So that goes that way. Okay? And how do I find my force of gravity?
Mass times 9.8.
All right, so let's do that. So I've got 50 kg kid, big kid, big kid,
Big boy.
too.
I didn't
times
wanna pull him
9.8, times 9.8. So what does that work out to?
490.
So I have 490 newtons going straight down. Okay?
Wait, how did you do that, you said? 50
Mass
times
times,
50 times 9.8.
Like nothing else you did.
Okay? So far, so good? All right. We have a normal force. The normal force works. So those of you that did not know this, there are a few of you that still did not know this. The normal force works perpendicular to the surface. So right there would be a right angle.
Right.
So I extend it down to here, just so that I can create a way in which I can solve math. All right? And the toboggan is going to move what direction?
Down the hill.
Down the hill. Mathematically speaking, I would say parallel to the hill, right? So I know it's going to go this way, correct? So therefore, I'm going to put this right here, parallel to it. And on this triangle right here, I can get my applied force. What is the slope that the hill is on?
30. Yeah, 30 degrees.
30 degrees, that's right here. That is also 30 degrees right here. Okay? That never changes. It's always that angle at the top. And like I said, I could show you all the math that goes with it, or you can just remember to not screw that up. Right? Put that at the top every time. All right. So, which one of the three forces represents my hypotenuse on this triangle? The force of gravity, the 490, right? Okay, where is FA in relation to that 30 degrees then? Opposite. So, opposite and hypotenuse is sine. So take the sine of 30 and times it by 490. Well, the sine of 30 is a half. So that makes that 245 newtons. But because we're dealing with friction now, we also have to be concerned with which force?
Normal.
The normal force. We didn't have to do that yet. Today's the first day that we had to worry about the normal force. So I've got the adjacent side and I've got the hypotenuse. So which trig function are we talking now? Cos. So take the cos of 30 and times it by 490. Cos 30 times 490.
424.352. That's
Yeah, 424.352. Did you use the cos thing, Ron?
for what?
Like, to find that? Because I didn't, like, Pythagoras theorem, and I got exactly the same.
I think that's I too.
You can
Yeah,
do
it works out because you don't have decimals on this one. That's why it works.
Wait for that one. Did
But-
you use sine 245?
Sine of 30 times 490. The sine of 30 degrees is a half. So we times that by 490, that's 245. Okay, so right now, I've got all the information I could possibly need to solve this question. That's all I needed to do. There's only one more step than what we had to do yesterday,
That looks quite intense.
and that was the normal. So now let's talk about the question. What does net force equal? What's net force equal?
FA
minus.
All right, let's start with that, Brock. F net equals FA minus FF. Is that any different than any of the questions we've done to this point?
No.
No, but we don't.
Okay.
You find that.
All right, so do we have the mass of the kid?
Yeah.
The sled? Yeah, what is it?
50.
50. Times A.
Boy.
What's his applied force?
245 newtons.
Wow.
Keep in mind that that's the voice weight.
Okay. And it doesn't give me the force of friction in the question. What does it give me?
It gives you the normal and the force, the
Kinetic friction.
Yeah.
You get kinetic friction.
The coefficient of kinetic friction, that's right, which is 0.15. I'm skipping A in this question for the record.
Just toss 0.5 or 0.15.
So, all right, what's my normal force equal to?
424 decimal 35 on times that.
And then divide by 50. And you get your acceleration.
3.624, no, yeah, 3.627.
Yeah.
I get 4 out of that. So that's 3.06.
Yeah, I got you got 3
I got 3.627.
Yeah, I got that too.
Good? Does that make sense to everybody today?
Yeah, and then we'd have to still put the angle.
No. There's no angle in this question. All right?
Oh, that's a good question.
Okay? So there's, like, really, as long, and this, in all honesty, this triangle doesn't change.
It looks scary though.
It doesn't change. It's the same triangle. I told you that a week ago. That if you can just draw this triangle below, it's the same every question. I can't change the question so that changes. All right? Okay, so far? All right, now, I'm going to change gears for a second here. Let me just have a quick look so I can make sure that, yeah. I want you to, I'm jumping ahead here, mostly because I'm excited about it, whatever. Page 181.
Holy.
181, really?
181. I'm not doing math here. I just want to talk. Okay, so one of the things that we're studying right now is we're studying friction. We're studying how tension affects things, something that's spinning. If you have a car going around a curve, all right? So the car is on the road right here. Real nice car. That's the back of it for the record.
That's the back?
Okay, let's try this again.
Like a boat.
You say a boat.
With wheels somehow.
A boat with wheels.
Oh,
There you go, good man. Seems pretty good.
What a hat. That's the back of it. Here's your tail lights.
There.
Okay. So you got a car, poorly drawn, but you have a car and it's on the road. How many, okay, so all of you have your driver's license or you have your learners or you've done some bit of driving or at least you've driven with your parents at some point in your lifetime, right? Yeah. For the most part. Okay. Have you paid any attention to the road and the corners that you go around?
Yeah.
And I'm not talking about in town.
Yes. When I go home, I turn. A road's like this.
Right.
So
I think what you're
But what do you notice about you speed up the road? No?
Slow
No.
down. That ain't it, Chief.
Yeah, you see corner?
Okay, let's put it this
Power
way.
turn.
I want you to think about this. How many of you driven out towards Lake of the Prairie, so through Yorkton, whatever, right? Or towards Yorkton. Okay, that's the one that I noticed more than any other.
Okay.
But if you look at the corner, when you're going, I'm going to draw it, so you're going out of town, you go around the corner, then you come down, and then you go down the valley, right? This corner right here. This corner right here.
Yeah.
Have you noticed the slope of that
Yeah,
turn?
it's like this.
Yeah,
Yes.
it's curved in. Okay, you have to.
It's curved in, right?
You don't have to slow down. It just
You
like
see
does
it
it for you. You just fall.
Right.
Yeah.
So what's happening there? Why? Has anybody ever seen NASCAR?
Yeah, they're tracks like this
That's
now.
awesome.
Right. Right.
Your momentum.
So the track in NASCAR is like this, and so your car is like
On a mean angle.
on a mean angle. You're right. Like to the point where if you stood at the bottom of the track, you'd almost be able to touch the track with your hand out in front of you.
How?
Like that's how sloped it is. But think about it. They're going 185 miles an hour around that corner. So why are they not sliding off?
Because the gravity's way too hard. They're
Friction
not going to
and
slide
gravity.
anywhere.
Because by changing this angle right here, all right, the gravity's not pulling this one straight down because you've got too much force going out to the side when you're doing those turns, right? So what it's doing is it's bringing the friction, bringing the angle of gravity into it so that it actually slopes this way. so that the car moves down towards it. And what it prevents it for, like they've got it figured, they'll have it done so that they'll know what speed can that car go at so that it won't slide up the track. Now that's no guarantee, right? Because you have to take into account what happens if it rains, what happens if it gets hot and the track gets warm and slippery when you got, cars going 500 laps around a 1 mile track. So they're doing 500 miles and their tires are going to get slick. They're going to lose their tread on their tires,
They'll
right?
change tires too. Like,
They'll change tires multiple times, right?
yeah.
So, because of the heat. But what they're doing and what that corner does at the valley there is it prevents you, because if you actually went around that corner with any bit of slickness to it, whether it's rain or whatever, you're going to keep sliding right off there.
Gone.
So what it's doing is it's changing that angle so that when you go around that corner, the gravity's going to pull your center of your gravity down a little bit more. It's going to change your center of gravity, and it's going to pull you towards the center of that turn. So we are going to look sort of at that. So like this turn right here, instead of you going like this, all right, and then like this, which we can't do that, right?
Not an option.
You're going to go in this direction here, but because of that slope, it's going to lean you towards the middle of the curve a little bit. And that's called centripetal force. Centripetal force is the force that pulls you towards the center of a circle. Just the same as when I was talking about spinning something on a rope. Okay, you twirl something around. I got my keys right here, right? Love to do this. Okay, so I have my keys right here. The mass is the keys themselves. But, all right, so if I spin it like this, it's not going anywhere. But the moment I let go, it's going to move off at a right angle in one direction. I'm not about to do it because I'll hit this or you or whatever.
So you do it,
right?
do it, magic.
But if I did it, let's say I did it, I don't know if it's big enough, it's not really big enough, but if I spun it around on the circle, horizontally speaking on the ground, right? So if I just do this on the ground, okay, it's going to spin off in that one direction. So that went off at a right angle to the center of that circle, depending on where I released it to. Okay, so the tension that I had pulling it back in, all right, the centripetal force was actually working away from me in that sense. The centripetal force works away at a right angle to where you're going. The tension pulls it in. So we're going to look at a couple aspects of this. We'll look at the cars, okay, and then we're going to also look at jet planes, okay. They talk about jet planes, so they pull. You never hear that? They pull 3 Gs or they pull 5 Gs. Or a roller coaster for that matter. They'll say that you pull 4 Gs. You guys ever heard of that? You know what 4 Gs means? Okay? G represents the acceleration of gravity. So that means you're pulling at 4 times the amount of gravity. So if you're to fall, you're going to fall at 9.8 meters per second squared, right? But if you're going around this corner on a roller coaster, or if you're doing it in a jet plane, you're pulling 4 or 5 Gs. That means that you're falling at 4 times the rate of change that you would if you were just to fall out of that airplane at that point in time.
Fast.
Okay? But it's not about fast, right? Because that is the rate of change. Your body is going, you're changing speeds at that rate, but on your body. So when they talk about pilots, they have to be able to, they have times in which they can fly. They have times that they have to be careful about blackouts and redouts. So a blackout will occur when all the blood rushes from your head out, and a redout occurs when all the blood rushes from your body into your head. And they both work the same way. But one is when you're going down too quickly and coming up, and the other one's when you're going up too fast and coming down.
Loop to loops probably give it to you pretty good.
Okay? So, well, exactly. So, most times, right? But they train for it. They train for it so that they can take more of it than a normal person. Now, I may be wrong with that. I think that I'll check, but I'm sure the blackout means all the blood rushes out, and the red out means all it rushes in. But so we're going to look at a little bit of that in the coming days. Okay? And it all ties in to this part of your physics. All right, when we're talking about force and gravity and the amount that it affects you. All right, so today, if you would finish those questions from the other day, anybody finish those 6 questions by chance?
6 questions. Oh,
Yeah.
The ones that you signed up for the assignment?
Yeah.
Didn't you say you show a movie called Concussion when you were
Now
Yeah.
we do momentum.
Momentum, that's what it was.
Okay, so you had 3 questions on page 158, Austin.
Oh.
3 questions on 158, 3 questions on 161 to do.
But what do you have to do with
Cameron.
Nice. The personal answers to this book.
And page 165 and 166 has the remainder of the questions that I want you to do, which will probably take you most of tomorrow as well. Okay? So there's 13 questions to do, and that's what you're going to work on right now. Okay?
158, 161, 165, 166.
You got half an hour to work on that.
161, 165, and 167.
It's a lot of brain power. I don't know if I can do it.
165 to 166.